Okay, so in this video we're going to be reviewing the basic stream functions that you can use in potential flow. Alright, so potential flow is a branch of fluid mechanics where the main goal here is to basically solve for these functions for velocity, right? And so what you're looking for in potential flow is basically very detailed pictures of what the velocity looks like at all points in space, right? And so you should be able to draw fields like this and like this using potential flow. Okay? And the way that we usually do this is through this function called the stream function. And so the reason we work with this is that, velocity is a little bit hard to work with in terms of governing equations because it's a vector quantity. And so we've developed this stream function which is scalar, to make it a bit easier to work with. And then once we have this stream function, we just take derivatives of it to get the velocity components, right? And so the way that we usually work with this is that stream functions have been studied for a long time, and so we know what some stream functions look like for some basic flows. And so what we can do then is we can take those what I like to call building blocks and construct more complex flows using these kind of basic flows. And we're going to do that through an idea called superposition. But before we go to that, let's review what our basic building blocks actually look like in terms of the basic flows. All right, so the first one that we have, probably is the most simplest one, is a uniform flow. And a uniform flow is basically a flow that just goes in one direction. And so the streamlines are just straight and they're parallel and they all go in the same direction. And so, we have the same velocity all throughout the flow. That's why it's called uniform flow. And so if you have a uniform flow purely in the horizontal direction, the stream function is just given by the velocity u times y. But what can happen also is that if you have a uniform flow that's kind of angled relative to the horizontal, you can account for that too in the function by multiplying by cosine and sine of the angle alpha here. All right, the next stream function we'll go over is a source and a sink. And so just like the name implies, source and sink is basically flow that's either pushing in you'll see the velocity streamline all converge onto a single point, or you might see them all diverge from a single point. So think about, I think the easiest analogy for the left right here is think of like the drain in your faucet, right? And so when fluid goes in there, it all kind of converges in there. And the source is just the opposite, right? And so source is if, the flow is all coming out from. And because we have flow that's kind of pointing out in a circle, it's kind of most natural to think about this in cylindrical coordinates, and so we express the stream function in cylindrical coordinates as well. So it's m over 2 pi times theta, right? Where m is a special parameter that defines the volumetric flow rate of the source and sink, and so you can think of it almost like the strength. And of course, the sign here determines whether it's a source positive or a sink negative. All right, so the next basic flow is a vortex, and so a vortex is a flow that rotates or spins around a specific point. Okay, and once again, because of the circular nature of this, it's most natural to think of this in cylindrical coordinates, and so our stream function is given in terms of r and theta, which in this case is r. Okay, and one thing I want to highlight about the vortex here is that it's a free vortex, where the velocity of the flow is strongest kind of near the middle of the vortex, and then it starts to decay outwards, right? This is to kind of help ensure that our flow is mostly irrotational, okay? So the middle of the flow obviously is not going to be irrotational because that's going to be spinning, but if you kind of sit along the flow elsewhere, because the flow kind of has this kind of property, you actually won't, you'll rotate along with the flow, but your body itself will not rotate, which is kind of how we define irrotationality. Okay, so the last basic flow that we usually use in potential flow is called a doublet. So a doublet is a little bit hard to explain. I think people kind of remember it for kind of how the figure looks, which is kind of like this hourglass shape with rotating flow. And the easiest way to kind of think about how it forms is if you take a source and you take a sink and you kind of push them together to a single point while kind of amping up their strengths. And a lot of people would think that, you put together a source and a sink and they would cancel out. And they do kind of near the middle, but then far away they kind of form these kind of circular patterns. And so the stream function for a doublet is given by this, where K here expresses the strength of that